So we just did the derivative of the natural exponential function. Now let's talk about going backwards. Well, remember, e is the easiest. So if the derivative of e to the x is e to the x, then the integral of e to the x with respect to x is e to the x. Of course, remember, plus c, but that's all there is to it. Now you may need to use a substitution, so maybe you think of it as the integral of e to the u with respect to u, but that's e to the u plus c. So that's it. Let's take a look at some of these integrals that aren't just e to the x and practice our exponential function using some u substitution. So I see e to more than just x. I call that exponent my u. Usually in your e functions, if you have more than just x in the exponent, that will be your u. So practicing our u substitution, u is 3x minus 1. du dx is 3, so dx is du over 3. Let's substitute. Our integral turns into e to the u. Dx comes out in its place, du over 3. What does that mean? Pull out the 1/3. Integral of e to the u du. E is the easiest. It's just e to the u plus c. Plug back in what u is. 1/3 e to the 3x minus 1 plus c. That's it. Now, because this one is so easy, instead of really having to do all this u substitution, you can kind of just think about this backwards. Here's what I mean by thinking about it backwards. Let's say I were taking the derivative of e to the 3x plus 1. Oh, plus 1. Did I write minus 1 down here? Let's fix that. Did I write minus 1 up here? Well, let's fix that too. 3x plus 1. Excuse me. So the derivative of e to the 3x plus 1, what do? I rewrite what I see, and I multiply by the derivative of what is the exponent. Where x is usually, and there's more stuff, the derivative of that is 3. Well, if I'm going in the reverse process, the antiderivative of e to the 3x plus 1, what's the reverse process of multiplying by that derivative? That's right, dividing by that derivative. So 3x plus 1 in the exponent times 1/3. Of course, remember the plus c. So I don't have to go through a fancy u substitution, although trust me, it's helpful if we just stay consistent. For example, in number 2, it looks a little bit trickier because of these trig functions. Focus on the e function. I see in the exponent more than just x, so let's call that tangent of x our u. Off to the side, let's say u is tangent of x. What's the derivative of tangent of x? Secant squared of x. This is looking a little skeptical that I'm going to be able to cancel out secant squared of x, but let's keep going and see what happens. Dx is du over secant squared of x. Let's go plug stuff in. Okay, so I'm going to rewrite e to the u over cosine squared x. Dx is du over secant squared x. Well, look closely at these two functions. What is the cosine function, or rather, what is the secant function? Either one you look at, they're reciprocals of each other. So if this is the reciprocal of that function, they divide out and leave you with 1. So what are we left with in this integral? E to the u du, and e is the easiest, so it looks exactly the same when we're done, plus c, of course. And then we plug in what u was back from the start. Yay! Let's peek at a few more. This is so easy that I had to search for some tricky examples. Now, we said when you have an exponential function like e to the x, usually you're looking for calling the u the thing that's in the exponent. Well, the thing that is in the exponent isn't complicated, it's just one letter, so we wouldn't do it in that instance. So something else to think of, all the other things we've learned. When we have a rational function, sometimes we call the denominator the u. Remember, we learned that recently. Let's try it. And by the way, sometimes you try something, it doesn't work, you try something else. Du dx, the derivative of our u, 0 here, e to the x is the easiest. It's itself, e to the x. Solve for dx du over e to the x. Let's go substitute it back into our integral. E to the x is still on top. U is on the bottom. Dx comes out, and in its place, du over e to the x. What happens? E to the x divides out. What are we left with? The integral of 1 over u du. I hope you recognize this from a few sections ago. This is the natural log of the absolute value of u plus c. Let's substitute back what u is. U is 1 plus e to the x, and there we go. We're done. Now, keep in mind that if it's multiple choice, you may not see the absolute values here. Why not? Because e to the x is always a positive function. Add 1 to that, that's still a positive function. So if you happen to see it look like this, it is also correct. Both versions are correct. Let's try a definite integral. Maybe you pause the video, give it a shot, come back and see how you did. First of all, I see that I have more than just x up here. So I can say, let's do a U-substitution. Or I can do my thinking backwards. E is the easiest, so it's e to the negative 4x. Doing the derivative, I would multiply by the derivative of this exponent. Doing the antiderivative, or the integral, I will divide by the derivative of that exponent. That's the fastest way to do this. Put the brackets 0 to 1. We plug 1 in first, then 0. How about we take out the negative 1/4 so we don't get confused by that? Plug in the 1, we have e to the negative 4 times 1. Plug in the 0, we have e to the negative 4 times 0. Let's evaluate and simplify as much as we can. E to the negative 4 minus e to the 0 is 1, minus 1. I can't do much more with that. It's simple, it's exact, it's good. Just a couple more that I want you to look for. When you have e and natural log mixed up together, think about, can you use your inverse process? And the answer here is yes. E to the natural log of x is just x. So rewrite this integral as the integral of x with respect to x. Well, that's just our power rule. X squared over 2 plus c. Done. Think about using ways to simplify. Properties, inverse. One last one to look at. Solve the differential equation. Fancy directions for doing things that we've already been doing. Solve, if it's a differential equation, it means it has a derivative. Solve the differential equation means get the equation to have no derivatives. Well, how do we do that? Go backwards, the antiderivative. So let's review what we did with this type of expression. Multiply to the other side dx. So dy equals 6e to the 2x dx. Get no derivative, or take the antiderivative. No derivative means I need the antiderivative. Boop, boop. Let's do the antiderivative of 1 with respect to y. Visible 1 in there is y. Over here, 6 is just a constant multiple. Pull it out, deal with the rest of what's in there. Deal with this e to the 2x. The fast way to think about it is that e is the easiest. I see itself. If I'm doing the derivative, I multiply by the derivative of the inside. If I'm doing the integral or the antiderivative, I divide by the derivative of that exponent. Don't forget your plus c. Other than that, you're basically good to go. You can clean it up a little bit, so I'd recommend doing that. 6 can divide by 2 to get 3, 3e to the 2x plus c. Did you have some fun with me? I hope you did.